morning. This is Dr. Suraj Prakash Harsa, faculty of Mechanical and Industrial Engineering Department at IIT Roorkee. I am going to teach the basic course of the engineering branch, like the solid mechanics, in which we are mainly dealing with the deformation or the whatever the mechanical forces are there, the mechanics of the rigid bodies and the deformable bodies. As you know, the solid mechanics as a subject is a branch of applied mechanics, in which mainly dealing with the solid bodies subjected to the various types of forces or loadings. So, if you want to categorize this solid mechanics, there are two broad categories, because here like there is a dynamics or static forces are there in the two solids when they are interacting or they are not interacting from the external excitation forces. So, solid mechanics, if you are dividing into two main categories, then these are mainly with the mechanics of rigid bodies. If we have rigid bodies, then what kind of mechanics is there within the rigid bodies or outside with the environment of rigid bodies. Or the second is the mechanics of deformable solids, or we can say rather it is the mechanics of materials, or we can also say that it is the strength of materials. So, these are two main categories under the solid mechanics. First of all, as we are categorizing this, the mechanics of rigid bodies, in which the mechanics of rigid bodies is mainly concerned with the static and dynamic behavior under external forces of engineering components. If you are dealing with any engineering problem, we know that there are lots of machineries are there, and these machineries are always under the operations of, let us say, like the high speed operations are there, or heavy load operations are there, in which we know that actually individual components of these machinery are just bearing the static or dynamic loads. So, we need to deal that actually what kind of deformations are there under the static and dynamic forces. So, primarily if we just concern with the surface level, we are mainly dealing with the internal or external forces and the motion associated with these particles and bodies, rigid bodies, due to these internal or external forces, because as we apply the forces, definitely there is a kind of motions are there of these particles of the component, or we can say the rigid bodies. First of all, as we are discussing in this, the force is the main thing. The variety of forces are there within the rigid bodies or with the environmental of the rigid bodies. First of all, like the tension forces, or we can say rather the axial pulling forces, which are always present in any kind of machinery or the general applications, just like you see here the towing ropes or lifting hoist. If you are just lifting any object through the ropes or hoist, we always facing the tension forces, because this is the axial pulling is there, while the second kind of the forces are also be existing within the object because of the load application is there through the compression. So, if we compress the things, the compression occurs in the legs of chairs or benches as you are sitting on it. So, these are all, we can say, the kind of axial forces are there, because you see the forces are acting along the one axis. Either you are just pulling the object through ropes or hoist, or if you are just sitting on the chair and these legs of chairs are just compressing because of the axial forces. So, these are the number of different ways are there through which we can apply the load on an object. So, again there are a variety of categories are there, under which one is the static or dead loads. These are, you see, the static means actually the magnitude and the direction of the loads are not changing with the time. So, they are just constant, or we can say if you apply, let us say, the 10 Newton of force, or we have an object of, let us say, some 10 kilogram. So, if you are just pulling, or if you are just sitting on a chair, then this kind of force is a static or dead loads are there, and that is also known as, you see, non-fluctuating loads, generally caused by the gravity effects, because you see if you are pulling or if you are sitting on the chair, the gravitational acceleration is always associated with the mass of the object. So, that is why the gravitational effects are always there under the static and the dynamic loads. Yeah, so because as we have discussed that actually these live loads are there. So, as we are just watching, like as the bridge is there under, like over the bridge, there are variety of these vehicles are just moving. So, these are just the live loads are there. These loads can be like the tensile or the compressive loads, but the magnitude and the direction of the loads is continuously changing with the time, as like the variety of trucks or the buses, or like the different vehicles are moving on as the bridge. So the real loads generally, like we can term as the live loads. The third way, the type of loading, the third way of loading is the impact or the shock loading. These are always caused due to the sudden blows. So you see, actually this is also one of the basic load, and if you want to design any component or any object, we need to focus that actually whether the load is the steady or it is an impact load or it is a shocking load is there. And the fourth way is the fatigue or fluctuating. As we discussed, the first one, that was the static and the dead loads. That means the magnitude of load is not changing, and it's not changing with the time. While you see the fatigue or fluctuating, it's always changing. The magnitude is changing, or the way of application of the load is always changing with the time. So fatigue, or you can say the fluctuating or the alternate loads, the magnitude and the sign of load changing with the time, and this is the main load is there. This is the main load through which the failure of machine always occurs. Yeah, so we are discussing about the loads. So again, you see, as we discussed, that if we have a rigid body or the deformable bodies which are subjected to the external applied forces, we need to assume that under these applied forces, externally applied forces, the system or the object will be in equilibrium position. So these externally applied forces may be due to the variety of reasons, due to the service conditions. If I have an object and it is, or rather I can say that if I have a machine element, always there are different service conditions are there through which the external forces are to be applied on the body. Second, due to environment in which the component works. Just like you see, I have an object which is just there in the open atmosphere. Always there is a kind of environmental force is there, or we can say the gravitational force is there on that body. Or if I have an object which is there within the machine, so what kind of, you see, the environment is there. That means if we have a lubricant is there, so definitely there is a less force is there. So it all the external applied forces are subjected to the condition where the what kind of environment is there in which the object is existing. The third is there through contact with the other members, through which you see, actually this is the basic thing in the machinery. All machine components are just connected with each other, and whatever the force or the torque, or we can say the speed, is transforming through this connectivity. So we can say that all components within the machine or the external what I can say the objects, they are always be associated, if they are always be associated with the contact, they always bear the different forces through the different contact members. The fourth one is there due to the fluid pressure. Fluid always, either we can say the Binance forces or the hydrodynamic forces are there. These forces always due to the fluid pressures, because you see the fluid is always having some sort of strength through which it always provides the impact or the steady state forces. So that's why these are also under the category of external applied forces. Then we have due to gravity or due to inertia forces. These are always presented, because you see, if we have the solid mechanics, then due to friction, always some sort of the frictional forces are there, or if we have the fluid, then always the viscosity or viscous forces are there. So these kind of forces always presented if the situation is like that or the environment is like that. So these are certain situations through which we can say that the external applied forces are there within the object. Now, as we discussed previously, that actually we can only analyze the different forces on object if the forces are existing within the object under the static equilibrium. What do you mean by the static equilibrium? Even the force is dynamic, or even the force is we can say the impact, we can only analyze the object if the system is under static equilibrium, because if the forces are not set up within the system, we cannot analyze the system perfectly. So either it is a rigid body or it is a deformable bodies, we need to, or we must apply the condition of the static equilibrium. That is the first and basic equation. Only after that we can analyze the system. So in this category, first we have the surface tractions, the force distribution applied to the surface of a body. Whenever the force is there, the important thing in the force is the application, means where the force applied, means what is the line of action is there of the force, because through which we can easily find out that what is the nature of force is there. So the basic thing in the force analysis is the line of action of force. The second is the body forces. If you apply the force, there is always the internal resistance is there. So, there are internal body forces are there which always oppose if you apply the external forces. So, there are two categories, if you can say the action of gravity, because if you put the object in the open atmosphere, definitely there is a gravitational force is there, and if the object is under static equilibrium, then definitely there are some internal body forces, they are resisting this action of gravity. The second is the magnetic attraction. These are all electromagnetic forces. So, these are all the internal body forces which always comes to the picture when you apply or when the object is there within these conditions or the environment. Okay, so we have an example here. We have an object which is under the variety of forces. So, we have different forces, and these forces are applying through the line of actions. As we have this P1, the line of action is this one, the P2, the line of action is outer towards, and this is there. We have P3 and P4. So, we can define the nature of forces through the line of action. So, how they are acting. So, like if you have like P1, P3 and P4, these are all compressive forces, though they are, the line of action of these forces are different, but they are all compressing the object. While we have this P2, the line of action of P2 is like this, but it is a tensile force. So, because there is an axial pulling is there. And if you want to see the internal body forces, then we need to cut through this plane. Let us say I have a Q plane, I want to cut this forces, I want to cut this object through this plane. I can easily visualize that under these forces, you see this object is under static equilibrium. So, how these internal body forces are set up to resist these all forces. So, we can also visualize these body forces as far as the surface traction, these forces. So, as we discussed about the forces, now we have the applied load or axial load. Axial load, the basic nature of axial load is actually that the load is always applied through the axis, or we can say the centroid axis. So, there are certain assumptions through which we can say that the axial load is applied on an object. First of all, this object, whatever the object we have, rather we can say the bar, rod or tube, it is always having a uniform and prismatic cross section. That means the cross section must be uniform, there is no deviation is there in the uniform cross sectional of this area, and it should be straight, or we can say rather prismatic. The second assumption which is must, that the material of either the bar, rod or tube must be homogeneous and isotropic. The third one, which is the basic condition, because we already termed that this is the axial load, that load whatever the P or F is there directly directed towards the axially directed towards the centroidal axis, either the tensile is there or it is either the compressiveness is there. So, we have one object, we can say it is a bar of length L, the axial force is there, axial forces are there towards the outer bound, towards the outer parts along the centroidal axis of the bar. Now, as you know that in the mechanics of deformable solids, the external applied forces acts on a body and body suffers deformation. So, there are two kinds of deformations are there in the object if you apply the force. One is the elastic deformation, one is the plastic deformations. So, because since the body is deformable, so we can distinguish these two terms as the elastic and the plastic deformations. And since we know that since under these variety of forces the body is under equilibrium, so from the equilibrium point of view, this action should be opposed or reacted by the internal body forces which are set up within the particles of material due to cohesion. And that is why you see the system is under equilibrium due to the, even under the variety of this forces are there, the system is in equilibrium part, because of the there are some certain resistive forces set up within the object. These internal forces give rise to a concept of stress, because you see we apply the force through different line of actions and the body is under equilibrium. That means there are some internal body forces are being set up. So, we can say that the intensity of internal resistive forces is known as the stress. So, this is the basic elementary definition of stress, that it always depends on the application of load. What kind of load is there, what is the nature of load, and what is the line of action of force is there. Now, as we discussed that the stress is always there, the internal intensity of the resistive forces, we can categorize these stresses according to the application of force like this, the direct stresses, in which there are two subcategories. One is the normal stress, one is the shear stress. Even in the normal stress, we can subcategorize, because this is nothing but the actual stresses, normal stresses. So either these are the tensile stresses or these are the compressive stresses. The next type of stresses are the torsional stresses. This is again the form of shear stresses, but within the rotational shaft. Then we have the bending stresses, that what kind of, you see, if we have a loading which always creating bending in the object, so the bending stresses are being set up within the object. Then we have the thermal stresses. If the object is there in the different temperature environment, then the thermal stresses are being set up due to the temperature. Then we have the combined stresses. If the object is subjected with the, let us say, the thermal and the external applied force is there, that means there is a change of environment due to the temperature, and the second, the forces, the different forces are there which induced or which created the environment of bending. So there are sort of, we can say that the combined stresses are always there with the combination of bending thermal or bending torsional, or we can say the normal and the shear stresses, which are under the direct stresses. So these are the variety of stresses are there, which can be induced in the object due to the application of force, variety of force. Now, as we discussed, the stresses as the internal resistive forces per unit area. If stress, the first case was there the direct stress, in which the two category was there, the normal and the shear stress. So if the stresses are normal to the area concerned, these are termed as the normal stresses, because the stress is nothing but the resistive force per unit area. So where these resistive forces are there, means what is the effective domain or effective area is there. So this will decide that what is the nature of force is there and what kind of stresses are being there in the object. So here, since the area concerned here is the normal to the object where the forces are being there, so that's why this is known as the normal stresses. We can also term these normal stresses as by Greek letter sigma. So sigma is nothing but equals to the force applied on the effective area divided by the effective area. Since this is the normal force, and we discussed that these normal forces are the axial forces through axis, so these are also known as the uniaxial state of stress, because the stress acts only in one direction, either the tensile or the compressive. So these are two categories in the normal stresses. Since the stress is nothing but the force per unit area, so there are the units like Newton per meter square, or we can say this is also the Pascal. So we can even categorize under subcategories that the megapascal is nothing but equals to 10 to the power 6 Pascal, gigapascal is 10 to the power 9 Pascal, kilopascal is 10 to the power 3 Pascals. Sometimes also, if you go to the FPS units, not in SI units, FPS units, then the unit of this stress is PSI, pounds per square. So there is also one of the basic unit which earlier we used to analyze the stresses. Now, as we discussed about the normal stresses, there are two categories, the tensile and the compressive stresses. These are all categorized just based on the line of action of force. So normal stresses can be either tensile or compressive, whether the stresses acts of the area or into the area. So if we are just doing the axial pulling, then these are the tensile stresses. If there is an axial compression is there, the line of action are at both sides of the object through one axis, and the compression is there, we can say these are the compressive stresses. The sign convention: if in a normal stress we are means if we are doing the axial pulling, these are the tensile forces, they are termed as the positive. Or if we are applying the compressive forces through the line of action of the central axis, we can say these are the compressive forces and they are termed as the negative. Because of the direction of the normal to the surface of the element on which it acts, we are always considering the same sign, the plus for tensile and minus for compressive forces. Therefore, a single symbol, because you see only these are all axial, means the line of action of either the tensile and compressive force along the same axis. So only we need a single subscript to define these type of stresses. That's why you see we are not going for the different 2 axis or 3 axis subscript to define the nature of force. Now the second type of stresses are the shear stresses under direct stress component. Now, let us consider the situation where the cross-sectional area of block is subjected to the distribution of force which are parallel. Now, you see the force application is not along the same axis. Now, it is the different axis, means there are two parallel axes are there, and at this point and at this point two different forces are acting. So, definitely there is a plane which is just shearing this the object at the contact points. So, rather than the normal, the area concerned is just parallel. So, the effective area is now parallel, it is not just exactly to the normal to the force. So, such forces are associated with the shearing of the material. Always there is a shearing is there at the effective area, and they are referred as the shear forces. So, the intensity of resistive shearing forces are known as the shear stresses, which is also we always define shear stress by Greek letter tau. So, tau is nothing but equals to the shearing forces divided by the effective area. So, these the tensile or compressive stresses or the shear stresses are always comes under the category of direct stresses. The stress, whatever the resulting stress is there on an object at any point in body is basically resolved into two components. One is under the dynamic under the direct stresses, one is the normal stress, which is designed or which is designated by the sigma, and the shear stress, which is to be defined with the symbol of tau. One acts, you see, because like the normal stress component is there, so it always acts the perpendicular, or we can say the normal to the area concerned, and other one, since it is a shearing part is there, so it is always acts on the parallel to the area concerned, and it is clearly defined with this particular figure. As we see the previous figure, now this is my the cutting plane. At this, the different internal resistive forces are there. As I told you, the different internal body forces are there. They are being set up due to the load application. So, there are two components. If we see this particular element of delta A area, this one is the normal component, which is always inducing towards the normal force. So, this is delta Fn is nothing but the normal resistive force. Delta Fs is my force which is parallel to the plane. So, it is termed as the shear forces. Delta Fs is the shear force. So, these two forces are there exactly according to the load application. So, that is why they are termed as the normal force and the shear force. This can be either tensile or the compressive. So, this delta F is the resultant force because of the presence of shear force and the normal force. Now, we can define again this, the normal stress vector, either the tensile or the compressive, is nothing but equals to delta Fn, the normal force, divided by the effective area, or the shear stress is nothing but equals to tau, which is equals to delta Fs. This is the shear force. As I discussed, this is the shear force along for this particular area along the parallel to the axis of parallel to the axis of this shearing plane. So, delta Fs divided by the effective area. It always acts, the normal stress always acts perpendicular to the effective area concerned, and the shear stress always acts parallel to the area concerned. So, we have now direct stress, in which there are two main components, one is the normal stress, one is the shear stress. Now, if we need to define the general state of stress at a particular point, then you see we need to take the small elemental area. So, stress at a point in material body has been defined as the resistive force, as we discussed earlier, internal resistive force per unit area, but you see this is not the exact definition of the stress. So, we need to check, because you see the area concern is very small in that case. Only we, you see, if you see the previous diagram, we can say that only these two means like variety of forces are there, but we are only concerned with the two directions. So, we need to check that whether it is fulfilling the exact definition of stress or not, or whatever the conditions are there with the stress associated or not. So, first of all, you see we need to check with the variety of directions. So, let us say we have a cube with the dimension of delta x in x component, delta y in y component, delta z in z directions. So, if I have a unit cube with these distances delta x, delta y and delta z in respective directions, then we can say that you see now we have total 18 elements to describe the stress. That means, you see these two components, that means the this normal stress and the shear stress is not at all fulfilling our requirement to define the stress at a point. So, you see now to before starting or before analyzing the cube, first of all we need to define certain things. Generally, you see there are certain notations are there to define the stresses. There are two types of coordinate systems. One is the Cartesians, just like XYZ, and the this polar coordinates are there, r, theta, z. So as far as the normal stress components are concerned, they are always there in the single direction. As we discussed, it is a uniaxial stress component is there. So they are termed as the sigma x, sigma y, and sigma z in the x, y, z directions. Or we can say, if you are taking the polar coordinates, then they are sigma r, sigma theta, sigma z. But generally in this subject, we are going to concern of the stress component in the Cartesian coordinate only. And as far as the shear plane is concerned, which is parallel to the effective area, so they are termed as tau xy, tau yz, tau yx, tau zy, tau zx, and tau xz. So these are the 6 components in different directions in the Cartesian coordinate we can define, or we can say also the stress component is there in the polar coordinate as they are showing here. So the general state of stress at a point involves all normal stress components together with all shear components. So there are total 18 elements which we need to describe the full stress for a single point. As we have seen, you see here, these are in the x direction, these are my axial stress component, these are again axial stress component, these are axial stress components are there in the x, y, and z directions. So you see these are all total this 3, 3, 3, 3, and these are all total 6 phases are there, and at individual phase there are 3 individual components are there in the respective directions. So there are total 18 stress components are there to describe the stress at a point. But you see, since I have taken the elemental the cube element which has a symmetricity, so we need to impose this condition that whatever the stress components are there in xy direction, this stress components in xy direction, which is exactly equals to this direction. That means you see we have the stress component, let us say this is in xx direction, this is xy direction, and whatever this is there in yx direction, they are identical. That means tau xy which is equals to tau yx, or we can say tau yz is equals to tau zy, or we can say tau zx is equals to tau xz. Sorry, this is xz. So this is these are all due to the symmetricity of the elemental area. Now, as we already termed that if we have a tensile stress, we always considered as a positive stress. If it is a compressive stress, then we always termed as the negative stress. So the same thing is there for the shear stresses. If due to the shear stresses presence, the object is tending to turn in the clockwise direction, we always considered the positive direction. And because of the presence of the shear stresses, the object is tending to turn in the counterclockwise direction, we always referred as the negative. So these are the directions of the shear stresses which are being set up in the object. We can consider simply whether it is a positive effect or it is a negative effect. Now, as we discussed, since these are the identical terms are there, so now we can reduce this 18 elements into the 9 elements. So now we have the total 9 components which we needed to describe the stress for at a single point. So now we have sigma xx, sigma yy, sigma zz, sigma xy, sigma xz, sigma yx, sigma yz, sigma zx, sigma zy. So these are the total 9 components. In these, you see there are 2 subscripts are there. The first subscript refers to the direction of the normal, like this x. So that means you see now it's clearly showing that actually what is the nature. That means the force is there in the direction of the normal or the parallel. The second subscript refers to the direction of the stress. That means you see the direction of the stress is exactly to the direction of the normal. That means I have the same stress, means there is a domain and the stress is being exactly in the direction of force. We can say these are the normal stresses, because we are tending that actually if this stress is acting in the normal area to the normal, we can say these are the normal stresses. So that's why you see sigma xx, sigma yy, sigma zz are always termed as the normal stress component. So only we need a single subscript to define these things. So we can redefine this, that sigma xx is nothing but equals to, we can replace by sigma x, sigma yy we can replace by sigma y, sigma zz we can replace by sigma z. And the other 6 component, you see the nature of nature of stress and the area domain is different. Now here you see actually the direction of normal is in x direction, while the direction of stress is in y direction. That means you see they are not matching. So these stresses are termed as the shear stresses. So we can replace sigma xy by tau xy, sigma xz as tau xz, sigma yx as tau yx, and sigma yz as tau yz, sigma zx as tau zx, and sigma zy is tau zy. So you see now actually we have 3 normal stress component and 6 shear stress components are there, which are being designated as sigma x, sigma y, sigma z in 3 respective directions, while tau xy, tau xz, tau yx, tau yz, tau zx, tau zy are in different planes of shear stress. Since you know that we have 9 different components including normal and shear stress components to describe a stress at a point, so that's why it is termed as the tensor stress, because you know like in a vector only we need the magnitude and directions, while here you see actually it is clearly showing that what is the nature of the stress is there at a single point of the variety of stresses. So that's why it is also termed as the tensor stress, and there are different 9 components are there on a single phase. So you see if we are taking the individual phases of the cube, we will find out that let us say in xyz there is a single phase in which sigma xx, sigma xy, and sigma xz, or we can say it is sigma x, tau xy, tau xz is there. So at a particular point P we have 3 different notations. So you can say that actually, since as we discussed in previous slide that there are different 9 components, and if we are taking the individual phases, we will find that how these stress are being set up within the individual phase of the cube. So this is the first phase. The second phase if we are taking, which is just parallel to the upper side, we will have sigma yx, sigma yy, and sigma yz, or you can say it can be termed as sigma y, tau yx, tau yz. The similar thing is there in the other directions, where the sigma z is the normal stress and the tau zx and tau zy are 2 different shear stress components are there in the respective directions. So these 3 slides will clearly showing that how the shear stresses are being set up and how the normal stresses are being set up in the system. So that's why you see we need exact 9 stress component to define the stress at a point P. So this P point is there, and these 9 components are there of the stress. So now you see if we are just taking the inclined plane, then how these stresses are being set up. So if we start from the first slide, we can see, you see here we have the xz plane where the this compressive normal stress is there along the lower direction. So that's why it is termed as minus sigma y, or we can say this is the another. If we are taking the another plane which is also the xy plane, we have the sigma z. Since it is in the compressive way, so it is termed as, since as I told you that actually if it is a compressive stress then it is termed as the negative. So this is minus sigma z and this is minus sigma y. And if we are just going with the another directions, or we are taking the another slots of these stress components, we can find out we have all this sigma x, sigma z, sigma y with the normal stress components. So these are all, we can say, the different parts are there where these stresses are being set up in the different directions, and also there are some other what we can say the stresses are there along the directions, which is also we can say the sigma p, which is the resultant stress component due to all stress components. So these stresses are there. You see if we have the parallel, then the stress we can show the stress by these directions, or if we have the inclined plane, then we can show the directions with these notations. So these are the different stress notations and the directions and on the straight and the inclined plane. So this was all about the stress. You see the normal stress, the shear stress component under the direct stress way. Now we have the strain. Whenever you see the load application is there, there is always the deformation is there in the object. That's why you see we are always analyzing the deformable bodies under the static or dynamic forces in the solid mechanics. So the another component which is very important to analyze the object in the mechanics part is the strain. If a bar or tube which is having a homogeneous material, and all those assumptions are to be applied here also, is subjected to a direct load. So due to, you see, when the load application is there, direct load application is there, the stresses are always being set up because these are all internal resistive forces intensity in the bar. So there will be a change in length, means always if it is a tensile, so axial pulling is there, so definitely there is a change in length. If the compressive forces are there, there is a compression is there or deformation is there in the compression side. So there is a change in length or in the diameter with the corresponding type of force, means what kind of a line of action of force is there. So if the bar has the original length L, or and due to the load application the changes in the bar, the change in the bar length is delta L, the strain is always defined as the change in length divided by original length. Since it is the length by length definition, so it has, there is no unit, it is the dimensionless and unitless component. Now the sign convention for the strain. Since you see the strain is also termed as what kind of load application is there, because you see if we have the axial pulling or axial compression is there, always there are the tensile and the compressive strains are there. So we can similarly as the stress, we can also define the sign convention exactly as the stress component. So tensile strain is there because of the axial pulling, compressive strains are there because of the compression of the object. So tensile strains are always termed as the positive, while the compressive strains are always termed as the negative. Since like the strain is nothing but the defined as the linear strain, normal strain or the longitudinal strain, because if you are pulling or if you are compression, this is nothing but the normal strain or the longitudinal strain, because the direction of the load is in the longitudinal way. The another type of strains are the shear strains, because the shear stresses are always existing within the object. So there is a deformation is there across the shear plane, these strains are termed as the shear strain. So an element which is subjected to the shear stress experiences the deformation, the tangent of the angle through which two adjacent slides rotate relative to the initial position is termed as the shear strain, and which is always denoted by the gamma, the angle of deformation. We have discussed the two important property under the solid mechanics. These are, one, as the load application is there under the equilibrium conditions, these are the load application under equilibrium conditions. We are having the too many stresses like normal stresses, shear stresses, torsional stresses, bending stresses. The another thing is since the load application is there, there is a displacement, or rather we can say there is a deformation is there, and to measure the deformation we always need the component that is known as the strain. So now we have the stress and strain. We need to, since you see these are two the consecutive components are there, wherever the stresses are there, the strains are always associated with the strains. So what is the exact relations? So now we need to define the stress strain relations, that what kind of load applications are there, what kind of deformation is there, then what is the relation is there within the stress and stress. Then you see it also termed as the load deflection or the load stress relationship. So now the method of analysis under the load stress or the load deflection relations. Now if you go with the method of mechanics, like mechanics of material or the solid mechanics, we always start with the equilibrium conditions. Like if you want to start any problem, first of all we need to check that whether this object is under static equilibrium is there or not. After checking those things, we need to go that what kind of stress and what kind of strain components are there. That means under the continuity equations, whether the stresses means the tensile or compressive stresses are there, or we have the shear stresses, then what kind of strains are there and what is the relation is there. So we'll discuss this part. The second thing is there which is also termed as the method of continuum mechanics and the elasticity, which is beyond our course, because you see actually we need to go with the elemental area and the volume of the component, and then we need to apply the compatibility equations. Then you see the different generalized Hooke's law is there under the condition of continuum mechanics and the elasticity. And the third part is there, that is also known as the energy methods, because you see since here the deformation is there and the load applications are there, so definitely there are different energy components are associated with the different particles and the objects. So we can also apply the energy methods, which is also known as the scalar methods, but since it will come in the later part of our course, so we will discuss in detail. Now we want to relate the stress and the strain component. under the different deformation conditions. So, first of all, the hooks give a law for the elastic deformations. As we discussed earlier that since if the load application is there, either the elastic deformation is there and the plastic deformation is there. So, under the elastic deformation there is a relation with the stress and strain. So, Hooke's gave the law under the elastic deformation. A material is said to be elastic if it returns to its original position. Means if you remove the load and body comes to its original state, we can say there is a elastic deformation. And if you see because of the load application, if a permanent set of deformation exists in the load or exists in the object, we can say this is the permanent deformation, or we can say this is the plastic deformation. So, these two elastic and plastic deformations are there. A particular form of elasticity which applies to the large range of engineering materials, at least over a pair of load range, produces the deformation which are proportional by the loads producing them. Always they are proportional to the load application, that how much load you apply, the elastic deformation is, the corresponding elastic deformation is there in the object. Since the loads are proportion to the strain, this also implies that the material are elastic, or we can say the stress is, because you see the load application is there, the internal resistive forces are there, the stress is there. So, we can say the stress is proportional to strain, or intensity of resistive forces, the body force is proportional to the corresponding deformation, because the strain is the measure of deformation. So, the Hooke's law, which is valid only for the elastic deformation, always gives the relation between the stress and the strain as termed as the stress is proportional to strain, or we can say the internal intensity of resistive force is proportional to the measure of deformation. So, this is there, you see the tau is proportional to the psi. So, this is my Hooke's law. Now, you see actually if we equate this, since you see there is a proportional constant is there. So, if we want to equate this, we have the new term, that is E, that is also known as the modulus of elasticity, that what is the magnitude is there of this elastic constant. So, but again you see this modulus of elasticity is again valid within the elastic region. So, within the elastic limit of material, Hooke's law is like that, or we can say the modulus of elasticity is nothing but equals to the stress by strain. Or we can say again, we can redefine this, the engineering stress, which is also termed as the simple stress or strain, which is equals to the normal stress. If it is normal stress is there, the load applied divided by the area concerned or the original area, and the strain is nothing but equals to the change of length divided by original length, or we can say since the change of length is there due to the load application, which is also termed as the deformation. So, the strain is nothing but equals to the deformation divided by the original length. Now, you see if we take an example of structural steel, means if we have a steel and there is axial pulling is there, we can define the stress strain relationship with that. So, you see now we have one axial bar is there. If it is, you see the axial pulling is there of this particular bar, which is having the homogeneous material and the isotropic material. This is also having the same cross sectional. This deviation is there because of the load application. So, we will discuss this part. Initially, it is just like as good as the uniform bar. So, as we apply the axial loading, maybe it is compression or it is the tensile pulling. Now, we have the corresponding stress strain diagram. So, you see initially if we apply the load, there is a elastic region is there, or we can say there is a proportional limit is there, which gives you the stress is proportional to strain, or we can say you see there is a straight line is there. So, up to this point, which is termed as the proportional limit, the stress is proportional to strain. Again, if we apply the load, there is a increase in deformation, there is also increase in stress, and it will give you up to, it will give a point which is also known as the yield point. Yield point is also come under the elastic deformation. This is the last point where if you remove the load, body comes to its original state. That means, this is the last point, or there is a limit where the elastic property of material remains closed. So, that is this. Then you see again we have a dip. This dip between the upper yield point and lower yield point is known as the yield plateau. So yield plateau is nothing but it gives you a straight relationship is there, that even if you apply the load, there is a deformation in this region, but there is a stress, there is a reduction in the stress. First of all, why there is a reduction in stress? You see, you are applying the load, but there is a reduction in stress. Why? Because you see, as we apply the stresses, there is a change in the microstructure of the object. There is a short period which is very short in the structural steel or any tensile, or we can say ductile material, which is a very short period, but there is a period where the material or the microstructure needs time to being set up. So this is the time where there is a chance to reduce the stresses. So here this is the plateau where there is a reduction in the stress, but there is an increase in the deformation. So this is this region or this dome is known as the yield plateau. Again, if we apply the forces, again there is, you see now increasing the stress as with the deformation increasing, there is a point where we are getting the maximum stress, which is also known as the ultimate tensile strength. So ultimate tensile strength is nothing but, or ultimate tensile stress is nothing but, this is the maximum stress being offered by a component before fracture. Then again, if we apply the force, again there is a deformation, but after a certain point we are getting the rupture, that means there is a failure. So now you see, now we have, there are two categories. One, we have the elastic deformation part, one we have the plastic deformation part. The elastic deformation part is this. The elastic deformation is here up to the Young's modulus, you know, because Young's modulus is only applicable where the Hooke's law is valid. So this is up to this part, there is, we have the elastic deformation, or in the previous diagram you see up to this point we have the elastic region, and this remain part is known as the plastic deformation. Then we have, you see, the two regions, one is the hardening region, one is the softening region. These two regions are always there within the plastic region. First of all, what is the hardening region, and second, what is the softening region? The hardening region is being, as you see, once we are approaching towards the plastic deformation, this is the starting point. As we are just approaching towards the plastic region, the object always offers the maximum resistive forces, because now you see the microstructure here is being already set up. So now there is a permanent deformation existing. This is the permanent deformation existing state is there. So here you see there is a maximum hardening is there. Once you see we are getting the maximum tensile strength, that means once the object offers the maximum resistance, beyond that you see it now it loses its hardness. So that's why you see now this is this part in which we are the object is not offering the maximum resistance, it is known as the softening region. So that's why you see these are the hardening and the softening region, depends on what kind of internal resistance provided by the object. Now you see we can even categorize those things with the different graphs. Like first we have the Young's modulus. So if you want to calculate the Young's modulus, which is only applicable to the elastic deformation, or we can say till the proportional limit, then this is our proportional limit. If you want to measure this thing, we need to apply the tangent on this graph. That means this E is nothing but equals to the sigma by E, that means the stress by strain. Then we have the proportional limit. Again you see, since Hooke's law is valid up to the proportional limit, so this is my proportional limit. I can get this stress of the proportional limit at this particular point. If we go beyond this, then there is no more the linear relationship is there between the stress and strain. Now you see there is a nonlinearity comes in the picture. That means we have now the stress is not exactly proportional to the strain beyond this point. So that's why it is known as the proportional limit. Here we can measure the proportional the stress at the proportional limit and the strain at the proportional limit. Now we have the yield strength. Yield strength is also the part of the elastic deformation, that is the last part. That means we can say this is the limit of the elastic region, or we can say this is the starting point. Beyond that there is a that is the starting point of the elastic region. So we have, you see now the yield strength here, upper yield strength or lower yield strength we can say, and this is the corresponding strain is there at both points. So this is my lower yield strength and this is my this is my upper yield strength, this is my lower yield strength, and this is the yield plateau is there. Now, you see again, if we go to the different steel, that is, you see we have an experimental stress strain plot for 1018 steel. That means, here you see we have the different carbon structure with that. So, here we can clearly find it out that actually this yield plateau is no more deviating. Here it is pretty like simple is there. That means, you see here the stress is not decreasing. That means, you see if we have less carbon, the less carbon component is there in the steel, it always offers more resistance. That means, you see this stress is no more reducing, though there is a deformation, but stress is not reducing. So, again you see we can clearly define that the stress and strain, here this is the proportional limit up to this point, this is my yield limit, here this is my lower yield limit and upper yield limit, this is this yield plateau is there, which is almost remains constant as you apply the load, and then you see here the hardening part will come, this hardening region is there, this is up to this point, you see this is my ultimate tensile strength, and then immediately it, because of the less carbon percentage, immediately after maximum tensile strength, this strength, it will go for the failure. So, this is the rupture. Now, since we are discussing the previous figure, this figure for the structure steel, and this figure for the different, this is also the structure steel, but different carbon composition. This mild steel or the structural steel is always termed as the ductile material. The ductility is nothing but the property of material through which it can extend up to a certain limit without failure. So, we can clearly distinguish the elastic and the plastic reasons for the ductile material, and whenever there is a rupture or the failure is there in the ductile material, we are getting almost the shape of cup and cone structure. So, this is the basic property of ductile material, which is always good in the tensile strength. So, they are having maximum tensile strength, that is why you see they can bear the tensile stress up to maximum. So, that is why you see we will find that the steel, mild steel or the structural steel has an application in the RCC or wherever the tensile load application is there, because they are more comfortable under the tensile loads. Then we have the cast iron. The cast iron, which is having more carbon percentage, always offers the damping property. That means, it is always good in the compression region. That is why you see the foundations are always being provided by the cast irons. So, what is the important nature is there? They are always good under the compressive strength, while mild steel or we can say the ductile material is always good in the tensile strength. So, cast iron, which is also under the category of brittle material, they are having brittleness, means they are not good under the tensile load, they are always good under the compressive load. So, if we are going for the axial pull, you see here there is a stress strain relationship is there, but it is not showing any like the elastic region or plastic region, or we can say there is no yield, upper yield or lower yield limit is there, or there is no proportional limit is there. Straightway as you apply the load, there is a stress component, there is a strain component, and beyond up to a certain point it will show some relationship which is non-linear, which is there is no linear relationship is there for the stress and strain component. It will show the non-linear relationship, and up to a certain point it will show something, then it goes for fracture. And at the point of fracture or rupture, we are having the zigzag or irregular shape at the fracture point. Like you see in in ductile material, we are always having a kind of, not exactly a kind of cup and cone structure, while for brittle material or the cast iron, we are having the irregular shape. If we take the another example of the aluminum, which is also a kind of ductile material, you see it is not exactly showing that where is the proportional limit is there, where is the upper yield point or the lower yield point is there, but we can generally get it, you see, as exactly there is a straight line is there. That means, you see, not much deformation is there, because you see this is a different carbon composition is there, so not much deformation is there, but there is the stress component, and beyond that you see there are, we can easily point it out that where is the proportional limit is there, and where is the yield point is there, and where is the maximum tensile strength is there, and then what is the fracture point, because we have the ductile material. So, this is for aluminum. Then we have, you see, the cast iron. So, as we discussed earlier, the cast iron is always provide good damping. That means, they are really good in the compressive compression. So you see the stress strain component, you see for tensile the straight way, if you apply the tensile load there is a straight failure, but if there is a compression or compressive loads are there, the compressive stresses are there in the cast iron, they are showing very good strength over this. Then we have the copper, which is also the some sort of the ductile material. So it always offers, you see here, if you see here, if you compress those things, then you will see, you will find these things here. So this is nothing but the stress strain characteristics for the copper. So these are all the graphs which shown that actually if we have different carbon composition or if we have different microstructures, then you see how these different regions are coming under the stress strain relationship. So these are all in the previous graphs, these are all the diagrams which clearly shown that actually there is an important part is there, that what kind of load application is there and how the stresses are being set up within the object and what kind of deformation is there and how we can correlate with the using of Hooke's law or modulus of elasticity or with the different strength like the ultimate tensile strength or the yield strength or the proportional limit or the fracture strength. So this part we discussed here. Now you see, as we see in the previous diagram of the stress strain diagram for structural steel, we have different reasons. So one reason was there under the elastic deformation. So area under the elastic deformation, whatever the elastic region was there, this area which is clearly showing here by blue line is also known as the modulus of resilience. Resilience always coming even if you see the impact loading is there or the steady state loading is there. So amount of energy absorbed by a material in the elastic region. So that's the important term. If the area which is go beyond this term, then it is not defined as the term of resilience. But whatever the amount of energy which is being absorbed while the axial pulling is there, so whatever the energy absorbed by the material, since you see you are applying the load, so definitely the particles are absorbing the energy because of the load application. So how much energy is being absorbed in the elastic region is termed as the resilience. So now the next part is the toughness. If we go beyond the elastic region and whatever the amount of energy is being absorbed by the material under the axial pulling up to the fracture point or up to the rupture point is known as the toughness. So there are two reasons, one is the elastic region and whatever the amount of energy is being absorbed by the material till elastic region is the resilience, and if you go up to the plastic region, that means up to the last point, that is the toughness. So these are the two properties of material, that how much energy is being absorbed. So it's a resilience and the toughness. So you see now we just want to conclude these things, that actually today we discussed about the initial part of the solid mechanics. That means you see how much, you see what kind of forces are there, how the what type of, you see the different mechanics is there of the rigid body or the deformable body, how the internal body forces are being set up, how the stress components are, you see, acted on an object. And you see the stress is always to be defined with the tensor stress. That means we need at least 9 components to describe the stress. And if you see, whenever the force application is there on an object, always there is a sort of deformation which can be measured with the one property of material, that is known as the strain. We can define the relationship between the stress and strain on the elastic and the plastic region. So that part we discussed. Now in the next class we are going to discuss more about that, actually you see what kind of other parts of stresses are there and how we can define the relationship if you see the object is not the straight bar, if the object is of a different geometry. Thank you very much. Have a nice day. Bye bye.
Thank you.